Okay, so today we'll be doing Mace Tac Toe. This was from the recent USACO US Open. Not really recent, it's like a couple months ago. But this was actually pretty hard. I started doing silver problems, and I've been struggling with silver, but hopefully, like after just practicing over and over again, different problems from different websites, hopefully I'll pass silver after the summer. That's what I hope. But yeah, so I didn't solve Mace Tic Tac Toe. I had to look at its editorial, but the solution is very interesting. So the idea is so it's both a maze and a tic-tac-toe board. So Bessie's on a location on this maze, right? Bessie, let's just say it's Bessie. That's a really ugly. Whatever, just imagine it's a maze. Bessie's on a location in the maze, and then she has a game state, a tic-tac-toe game state. And so the idea is whenever she moves, so in a cardinal direction, so north, south, east, west, whenever she moves onto one of these letters, the letter would give the O or the what do you call it? The wow, I can't. Oh, index. One. The X and Y index, or Y and X index, because computer science are flipped. You'll also notice that it's not X and O, it's M and O. In this game, you have to spell moo instead of the common X, X, X. And you'll notice you can spell it backwards and it also works as well. I don't know what that is. So, your purpose is to, knowing that Bessie can move, and these are walls, by the way, you can't pass through walls. You're finding the amount of winning board configurations Bessie can reach, starting with an empty board. And so you'll notice how hard this problem is. Well, no, there's an easy solution. There's always an easy solution. There's always a solution. You'll notice that Bessie can move like into these pockets, move out of them, and then just go to a random like segment, right? Maybe Bessie just decides to skip 011, and then she'll just go here, and then go maybe take M22 and M13. Oh, by the way, if a letter is already filled and index is already filled, it doesn't override it. It just nothing happens. So, like you'll notice, like Bessie can go in just these weird like patterns where she can go like down, right, up, completely skip this, come back, and then just randomly take this one. Like you'll notice the winning examples. This, oh wait, yeah, here. This and this are the exact same, except Bessie just decides to get this one for just no reason. Okay. Oh, by the way, the game stops right after she wins. So as soon as she lands on N33, she wins. So like in this path, she'll just go, let's see, 1-1. Okay. Oh wow. Okay, wait. Let me check something. Okay, so in this path, Bessie just decides to wait. Yeah. Let's see. Let's go this path and wait. Yeah, this path and this path. So these two. So in this path, I think this is like the optimal path actually. So Bessie just goes up and then goes down, takes 032, which is this O, which is required, and M33 and 031. Right? 31. Actually no. M33, which is here. What is O2? Oh, okay. Sorry. I'm doing this wrong. So Bessie goes up. So for this right here, Bessie goes up, takes 1-1 right here, knocks that out. Goes 0-2-2, knock that out. Goes all the way back, goes 0-3-2, knocks that out, and then M3-3 knocks that out, winning the game. Here, the only difference is that when she reaches 0-2-2, right, she just goes and picks up, or actually no, the only difference is when she goes back here, wait, let me see. Oh, okay. The only difference is when she goes to 0-2-2, you'll realize that she just picks up 1 M13 for just no reason. Okay, even though it's not optimal, it still is a different winning board compared to that because there's just one random M. And it's hard to compute that. And it should have been a red flag to me because one, this is a Brian Dean problem. He's like I guess like chairman of computer science at Clemson University, something like that. And you'll notice with his problems, it's actually kind of funny. All of his problems are just brute force. Well, to my knowledge, I haven't seen his like gold or whatever higher. It's just brute force. It is just brute force. And I should have done that. I don't know why I was thinking of some like crazy DFS segment tree. I just learned segment trees because I love learning new stuff. But holy smokes, I'm so stupid. Anyways, so you basically just brute force it. I just gave a hint. And so that's with a lot of Brian Dean problems. You just brute forces, but the hard part is through implementation. How are you going to brute force it? How are you going to go through every single possibility and record every single thing? And remember, you have to keep like a set, right? You can't have like you can't count it over and over again, because sometimes you'll get like this, you'll get a different path but the same game state, right? So okay, let's show you the parameters of how this is going to work. Can I like okay, ruler last sub select. Okay, whatever. Let's just start. So you want to keep track of the location of where Bessie is at currently after movement, and you'll also want to keep track of the game state. So what I mean game state is the board configuration. Got it? So this is a different game state than this. Yeah, this is the editorial. So I just want to quickly look at it before I don't say anything stupid. Okay. So how are we going to brute force this? How are we going to go through every single possible path Bessie can take? Well, it's actually really simple. You just, or well, you can tell this problem is a flood field problem because it has like a graph, kind of, not really necessarily a graph, it just has a board, and you go up, north, south, east, west. And you basically have just no restraint, and you just let it fly. This just means it recurses to, or I'll just draw it out actually, from ij. This just goes north, south, east, west. God, what the heck is that? It just goes north, south, east, west, north, south, east, west, blah, 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 recurse. At first, now, here's the deal. I was like, okay, you know, usually with these problems, like, you usually have like a visited Boolean array where if you've already visited an index, right, when you do DFS, you've already visited an index, you would already you would end the statement. So I go up here, right, visited, or I've already so I'm here, right, let's say I just go up, 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 and I'm checking. Okay, this says a wall now. This says a wall now. This I visited, so that means no. Down here, we don't have a visited Boolean array. We don't. This is something for later. We'll see why. But yeah, there's no visited Boolean array. So how do we stop or break the flood fill? Well, game states. So basically, if you've already seen a game state, or you've already seen okay, Bessie can go in like crazy patterns, right? As you notice, this is completely different than this. And she can also have like the same game state, but in different location. You'll realize that after some examples. It's hard to break them up. So remember, location and game state. And so this is the basis for how we're going to brute force this. Right, so let's repeat that. She can have different, she can have the same location, but a different game state. And she can also have a different location for the same game state. That makes sense. So remember, game state is board configuration. So how are we going to compute it? Okay, don't worry about this. Yeah, it looks a lot. And if you don't like C++, I'm sorry. So this is the board. This is exactly how the editorial uses it. I just like rewrote it in my fashion. Or this is actually Benchy stuff. So you read and input, you find Bessie. So this is Bessie in Y and X. Remember, computer science, it's backwards, Y and X first. So yeah. So what's cool about this is it just reads 3 at a time, and you can just do, you don't have to iterate by 3. Like simply inputting this is such a bother, but they make it look so easy in the editorial. But so you input it, right, and yeah, you find Bessie, and you do flip it. Now we keep a set answers of possible game states. Now the cool thing about this code is that it sets game states, like storing a game state or like a possible game state seems impossible. Okay, because you have to store 9 different numbers, right? If you just change these, okay, you can change like an empty slot to 0, M to 1, and O to 2. And simply storing 9 numbers is just so, like, to every single possible game state is very, very space consuming. And we only have 10 to the 10, or more like 10 to the 9. Usually if it's 10 to the 10, it's like memory limit. But you only have 10 to the 9th, or usually this amount of megabytes. I don't know if it says the amount of megabytes, but yeah. So that's very space consuming. But the cool thing is, with this code, or from the editorial, you store it with one number, just one integer, and it tells you exactly what it's going to be. So, okay, that'll be cool later. So once you think about it, right, let me just erase everything. So once you realize it, okay, so in order to do that, we have to find the max amount of game states that there possibly is, right? So in a 3x3 tic-tac-toe board, you have 3 possibilities: empty, M, or O, right? That's 3. 3 to the power 9 because there's 3 times 3 times 3 times 3 times 3, dot, 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 dot. So 3 to the power 9. And we also have location. Remember, location and game state. God, what ugly letters. Okay, and game state. And so since n is 25 max, it's 25 squared. Right, because you have the length of 25 multiplied by the width of 25. So you can be at one position, and you can have 3 to the 9 different game states. That's the reasoning for this. Okay. Cool. Now, on to the code. So like I said earlier, it has to be float fill because you have to recur somehow. And actually, just float fill makes it nice. That's really the reason why. So yeah, this is the visited boolean. Although I said there's no visited, technically this is like storing the past game states that are viewed. This is 3 to the 9th, by the way. I'll write that in as a comment. Pow3, this is just a way to store all the powers of 3. And this will be helpful in storing game states. You'll see why. It's so cool. I should have thought of this, man. It's like, I think I could think of this as just like so cool. So, okay. So you'll be wondering, the first index, so 0, stores like what it is. So it's this guy. And it tells you what it's going to be on the tic-tac-toe board. Cool. Yeah. So let's just run it over. Okay. So we got this. We found Bessie. We know where she is. And we'll start with the float fill where Bessie is. And so, okay, there's a wall. Oop. And 0, game state 0, this is B. B is actually 0. Float fill 0. Okay. Yeah. So for the flood fill, we'll store 3 parameters: I, J, location, and the game state. B is big game state. And so if equals M or 0, so if it doesn't have a letter, doesn't matter because we don't need to care about game states in that case. R. And so this tells us the location. This would be 0. Yes, yeah. This also changes it to 0 index as well. And index, R times 3 plus 3 plus C. This will be very helpful in storing game states. So row times 3 plus C. Let's see, let's just play around with that. So row times 3 plus C, so this is row 0, 0. Row times 3 plus C is 0. 1, 2, 3. Oh, wow. It's just basically base 3. Or not base 3. It just helps give an individual index for each person. And you'll notice it's like, for me, it's helpful to think of it as like base 10 as numbers, where it's kind of, yeah. You'll think of every number. It's just, if you think of it R as C in 2 digits, it's R times 10 plus C. So 11 would be like the 2 digits are 1, 1. 11, 1 times 10 plus 1, and that's 11. That's what you get for the decimal version. I don't know if that's capable or understandable. Current. So this tells us what are we going to change it to. So like how this will help add to the large number that's B. If you print out B, it's ridiculously weird. But it helps you think of B. And remember, this is also lexicographically sorted, or lexicographically ordered. So this is game state 0. This is game state 1. And that's how it's ordered. Game state 2. And it's ordered that way. Yeah. And so let's say you want to find out, like, maybe, yeah, so this also gives you that. See, look how weird B game state is. You know, it's hard to like dissect that, but how game state is ordered is how game state is ordered is, let's say you want to like MO, right? It's so, okay, this is 2 plus 0 times blah blah blah, 0 times, remember this is 1 2 or 0 1 2 or 3, 0 times 3 to the 1, 0 times 3 to the 2, and this is 1. So 1 times 3 to the 4th. And this helps it so that there's a unique game state for every number. 81. And you'll have to add this for every single one. And if you have full numbers, I think it's like M, 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 or actually it's O. O, 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 O. That is 2 times 3 to the power of 9. Which is actually, is that right? No, it's just 3 to the power of 9. Yeah, it's just 3 to the power of 9. Okay. But yeah, it makes a unique game state every time. And then right here, this allows for the change. So yeah. Okay, it's really hard to break it down. So B takes out the amount that's going to be changed within B. This is going to be so hard to understand. By the power of 3, then you add the amount that you're going to change. So like, yeah, remember how like each one is, this is a really hard problem. Why did I choose it? But 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. And you know how each one has its own little part? That's how you like identify each game state, as well as how you can change it. And so you subtract that by that, and then you put in your new one. And so let's say you want to change from M, M, which would be, or actually, you want to change from 0 to like an empty to M, which is 1. You'll add 3 to the 4th to it. That's how you change it. And then this is kind of what it does. You also have to subtract it from the guy greater, just in case if you have like if it goes over or adds up to it. I think that's what I'm getting from it, but this is probably the hardest part of the whole thing right here. I'm not gonna be. I'm gonna be real. I don't know if I can do this in a contest. It is really hard to like organize game states for me, but I feel like it's kind of like I said, base 10, and you just have to get a really good feel of numbers through this one. But yeah, and then so win, this also tests it a win case, so it's actually kind of cool. This also shows you how the game state works, the number, and it breaks down like what mod 3. So if it's 1, it's M. If it's 2, it's O. And like I said earlier, everything is divided by what it is. So it just iterates through every single part of B, right? 6. Just iterates through every part of B, and you'll see that what integer it is, what letter it's going to be. It breaks down for you. I also did a nice little print thing too, so you'll see later. And this is just a really easy check. This is like basic stuff. Check if it's Tac Toe or it's moo. Actually, yeah, it's pretty easy. So the cool thing is seeing the code. So I made a extra like helper function to help notice what it is. How long is this? God, 22 minutes. What the hell? Well, it is a hard problem, and like this part, I know I didn't explain well, but you gotta get a feel for numbers to understand. So yeah, I got this game state, and 2, 2, 1. This gives you this. Like it literally prints out the tic-tac-toe board for you. Look how cool that is. Yeah, so this is also in lexicographic order. Cool, really cool. Yeah, so here, here. These are all the different possible win case scenarios. And you know this has gone through every path because it's gone through every single possible game state. Yeah. And I wish I can explain this better. It's like you take a part of B that is, like I told you, each index has its designated 3 to the power. And so take that part of it, right? Like if it's empty, it's just going to be 0. If it's not empty, it's going to be 3 to the 4th times 1, right? Or if it's M. And if it's if it's combined, or if it's O, it's 3 to the 4th times 2. Yeah, that's kind of how it works. And yeah, but gosh, it's a really cool problem. It's just the idea is not hard. It's just brute force, and making game states, identifying game states. The hard part is implementing it. But this problem was really fun. I loved it a lot, and I'm probably gonna make a video of the next 2 problems, which are not as hard, but they're still fun. And I actually starting to like USACO problems. But yeah, let me just do a little satisfying submit. Let me just make sure I'm not submitting any garbage. I'll just make sure this test case passes real quick so you can see the status point in green at the end. I know everyone wants to see the green. Well, I do at least. I don't know. Ah, shit, I'm still printing out stuff. Why am I still printing out stuff? That's this little bit. So yeah. Also, every time you get a new game state, you want to put it into the answers. And the reason why it's a set, it's so you don't have to double count or count two game states that are the same. But yeah, this problem is really cool. I had a lot of fun with it. Although I didn't solve it. Sucks. Still loved it. Would do again. Okay. Basic Tac Toe, CPP. Grading in progress. Please. Yumbo, please. There we go. That's the end of the video. Thank you for watching. Goodbye. Have a great summer.